Right, so hi, I'm Ken Holstein, and today I'll share some work together with my incredible mentors from Microsoft Research, investigating industry product teams' needs for support in creating fairer machine learning systems. So, by fairness in machine learning, I mean very broadly cases where systems favor certain individuals or groups over others in systemic, undesirable ways. So, for example, a facial recognition system might systematically exhibit poor performance for certain subpopulations. Or a search engine might systematically pull up arrest record ads for names associated with black people, but not for others. Or a chatbot might learn from social media data to make extremely racist and sexist remarks. Or an image classifier might assign historically offensive labels to images of certain groups. So all of these examples actually happened, and these kinds of stories are being picked up by the media with increasing regularity. A range of academic research disciplines have picked up on this, and there's been a huge surge of papers on fairness in machine learning. We're also seeing many high-level calls to action aimed at those responsible for developing and maintaining these systems or for regulating their use. Beyond these calls to action, a lot of machine learning research has focused on the development of algorithmic methods to monitor and mitigate undesirable biases in machine learning systems. And as the field matures, we're starting to see the development of integrated toolkits with the aim of making existing algorithmic methods more widely accessible and usable. But moving forward, if we want these sorts of tools to have a positive impact, it's crucial that their designs are informed by an understanding of actual needs for support from those who will ultimately use them. Despite this widespread attention to biases and unfairness in machine learning, we know of only one prior study investigating practitioner needs. So at last year's CHI, Michael Veal and colleagues presented a study of challenges faced in high-stakes public sector contexts, such as predictive policing and child mistreatment detection. In the same spirit as that project, we focus here on understanding how we might better support practitioners in industry contexts. And to our knowledge, this is the first systematic investigation in the literature of industry product teams' needs for support in developing fair machine learning systems. So we ran up against a lot of challenges in doing this work. It turned out to be really hard to gain product teams' trust so that they would talk with us about their struggles with fairness in well-known machine learning products. Some of these fears are captured in the quote shown here from one of the practitioners we interviewed, who perceived researchers as often critiquing products from the outside, rather than engaging with product teams to solve problems. And this is a point that I'll come back to later. So when we first started to talk with product teams at a major technology company, we began to notice a mismatch between their needs and what existing fairness toolkits tend to provide. Building on our initial observations, we conducted more in-depth, semi-structured interviews. We conducted one-on-one interviews with members of 25 product teams across 10 major technology companies. As you can see from this slide, these teams span a variety of areas. In addition, where possible, we've tried to interview people with a range of roles on these teams, from product managers to data scientists to those more focused on data collection, for example. And that strategy turned out to be useful, as we've sometimes heard different perspectives from people at different levels of the same team on that team's challenges and needs for support. Our aim in these interviews was to better understand teams' current practices around fair machine learning, and also to identify opportunities to better support these processes at critical decision points. For each major decision point, we asked participants to recall specific challenges they'd faced and to describe how they'd handled them at the time. And we also probed participants' perceived needs for additional support. In our sampling and analysis, we took a grounded theory approach, extracting common topics from interviews and iteratively grouping these into higher-level themes. Finally, we supplemented our interviews with an anonymous survey of 267 participants who work on machine learning-based products in a range of roles such as data scientists, UX researchers, data labelers, and product managers. Our meta takeaway was that there are indeed major disconnects between the literature on fairness in machine learning and industry teams' actual needs for support in developing fair machine learning systems. Although we interviewed practitioners from a range of technology areas and application domains, several clear and consistent themes emerged, which were further reinforced through our survey. And given limited time, I'll summarize just a few of these themes in this talk. So one of our most striking findings was on the role of data. The fair machine learning literature generally assumes that data sets are pre-existing and fixed. The focus is then on designing fair models or algorithms to optimize quantitative fairness criteria. In contrast, industry practitioners often have some control over their data sets, and this is the first place they're likely to turn when attempting to address fairness issues. Several interviewees voiced needs for tools that can actively guide data collection efforts to mitigate fairness issues or even to avoid such issues in the first place. For example, interviewees highlighted needs for tools that can diagnose whether they should focus their attention on their models or their data, and if the latter, how much additional data they might need to collect from a particular subpopulation to address the issue. As another example, the quote shown here is from a machine learning developer who works on automated essay scoring for grade school students. To collect their training data, their company has a team actually go out, connect with schools, and collect student essays that have been graded by teachers. But they found that in the data their team collects, it's very rare to find examples of African American students being scored highly. So they really want cost-efficient ways to guide their data collection processes to ensure that they collect more such examples. As a second major theme, interviewees often expressed anxieties about their own blind spots. For example, the fair ML literature typically assumes the subpopulations we want to be fair towards are already known, or even defined by law. In contrast, many practitioners worried that they have blind spots here, and express needs for support in identifying which subpopulations to consider in the first place when thinking about fairness in their particular systems. Some teams currently have a practice of getting together and trying to imagine everything that could go wrong with a particular system so that they can make sure to monitor for those issues in advance. But inevitably, once a system is deployed in the real world, the public discovers issues that the team failed to anticipate. And some interviewees further stressed that the most relevant subpopulations may be heavily application dependent. So for example, when automatically evaluating students' writing in certain educational contexts, you might care about being fair towards non-native English speakers. For these reasons, both interview and survey participants noted that it would be nice to somehow pool knowledge of potential pitfalls, for example, across teams with different cultural backgrounds, who may have complementary knowledge and also complementary blind spots. One way to facilitate this pooling might be to create mechanisms for greater sharing of test sets across organizational boundaries, which encode nuanced knowledge that no single team is likely to have. Some interviewees also shared stories about their own cultural blind spots. So for example, we spoke with one team working on a globally deployed image captioning system that's meant to recognize celebrities. The team had received several complaints from non-US users, since the system seemed to work well for US celebrities while misidentifying or misgendering celebrities from their countries. The team mentioned having great data on American celebrities, but having trouble gathering data on celebrities from other countries because their team members simply don't know what those celebrities look like and have trouble telling them apart from others. A few of the teams we spoke with tried to mitigate some of these issues by trying to recruit more diverse teams. But again, especially in cases where machine learning products are deployed globally, effectively addressing unfairness can depend on really nuanced cultural and domain knowledge that no single team is likely to have. So one promising direction for future research may be to support teams in the ad hoc recruitment of diverse team external experts for particular tasks, where in some cases relevant expertise may simply mean being immersed in a particular cultural context. As another major theme, while most machine learning fairness metrics have been designed for classification tasks, we found that product groups grapple with fairness issues in a much wider range of applications. So, teams often reported struggling to make use of existing quantitative fairness definitions and metrics that have been proposed in the literature. For example, with chatbots, the unfairness of a conversational move can depend heavily on the surrounding conversational context, yet this can be challenging to quantify. And in domains like healthcare and education, the unfairness of a machine learning system's behavior might depend on its real-world impacts on health or education outcomes. But there may not always be a straightforward mapping between a machine learning system's causal impacts in deployment and performance metrics of a constituent model. In addition, we found that although most existing fair machine learning methods assume access to individual demographics, several of the teams we spoke with are only able to collect demographics at coarser levels, such as neighborhood or organizational level statistics. And this is for legal reasons in some cases. So, they struggle with fairness auditing, and in most cases, these teams simply gave up on trying to improve fairness in their systems. Some interviewees in this situation shared stories of times their teams had tried to infer individual demographics in order to audit for fairness, but this practice can actually introduce new harms. The interviewee quoted here shared that their team had developed a tool called the Sethdomator, a sex and ethnicity estimator. However, at some point while developing this tool, the team recognized that the use of proxies to infer individual demographics could itself encode harmful biases, and so they would then need some sort of tool to audit their auditing tool. So this Sethdomator project was ultimately scrapped for that reason. To share just one more major theme, we found that even when serious issues are detected, teams can be very hesitant to address them for various reasons. And among these, several participants shared prior experiences where, after making changes to models or datasets to improve some aspect of fairness, the system changed in subtle, unexpected ways that harmed users' experience, yet weren't reflected in any of their model performance metrics. And because of these concerns, teams often reported implementing many local band-aid fixes, rather than trying to address the root cause of an issue. In part because making broader changes came with the risk of unpredictable, system-wide side effects. But a trade-off here is that these local solutions also tend to be quite brittle. So let me wrap up by summarizing a few interesting directions for future collaborations between HCI and machine learning researchers. First, we need research on how to support practitioners in collecting and curating data sets that can support fairness in downstream machine learning models, since practitioners often do have control over their data, and they tend to seek out solutions there first. We also need application and domain-specific methods and tools, since the meaning of fairness can be highly domain-specific. While machine learning researchers are often incentivized to produce domain-general solutions, we found that practitioners often could not apply these in their actual contexts. Third, we need more research on how to support effective and data-efficient fairness auditing in scenarios where teams only have partial access to individual demographics. Fourth, we need more research on usable tools for fairness debugging, targeting authentic debugging tasks faced by practitioners. And finally, our findings point to needs for new kinds of prototyping methods and tools that can more effectively surface fairness issues in complex machine learning systems. So, while I was only able to cover a handful of findings from our study today, many more are covered in our paper. As one final note, moving forward, I think it will be really important for fairness researchers to work alongside product teams, as well as those affected by these products, to co-design processes and tools that are effective in their particular contexts. By engaging with the particulars, these kinds of co-design efforts can raise interesting design and technical challenges, which can then also productively guide more basic research, as well as theoretical work in the field. All right, thank you.